Hi, my name's Mr. Ray. This is the second climate change video. And in this video, we're going to talk about carbon dioxide, radiation, and the greenhouse effect. Now, we know that greenhouse gases will absorb certain wavelengths of infrared radiation coming up off the Earth. So as the Earth absorbs sunlight and heats up, it gives off infrared radiation. And then greenhouse gases will absorb some of that infrared radiation as it comes up off the Earth. Carbon dioxide molecules strongly absorb radiation around the 15 micrometer wavelength. The size of a carbon dioxide molecule, now a picometer is a trillionth of a meter. The size of a carbon dioxide molecule is 330 picometers. Because that's the size of a carbon dioxide molecule, it takes this many carbon dioxide molecules to cover 1 square meter of ground. So if you want to completely blanket 1 square meter of ground and absorb all the radiation that's coming up from the ground in the 15 micrometer wavelength, you need this many carbon dioxide molecules, 9.18 times 10 to the 18th power. If you take your square meter of ground and go up a meter to make a cubic meter of air, if you have a cubic meter of air, you'll find at today's concentration 7.08 times 10 to the 21st carbon dioxide molecules in that cubic meter of air. If you compare that with the number of carbon dioxide molecules it takes to cover the whole square meter, you'll realize that in 1 cubic meter of air, there's almost 1,000 times the number. See, this is 1,000 times larger than this number. So there's almost 1,000 times as many carbon dioxide molecules as what you would need to cover your whole square meter. And what that means is for every single location on the ground within your square meter, within each square meter, every single location at today's concentrations, now our concentration is about 405 parts per million, but at a concentration of 400 parts per million, there's 770 carbon dioxide molecules in the first meter over that one location, waiting to intercept the radiation coming up off the Earth. If we were to cut this in half, go down to 200 parts per million, we'd find that there's still 385 carbon dioxide molecules above every single location in the first meter of air waiting to absorb radiation coming up from the Earth. If we were to double the concentration, go up to 800 parts per million, we'd find 1,541 carbon dioxide molecules on average waiting above every single location within our square meter, waiting to absorb the radiation coming up from the Earth. So what are the chances that radiation coming up off of the ground is going to encounter a carbon dioxide molecule within the first meter as it comes up off the ground, within the first cubic meter? Let's start with 200 parts per million concentration of carbon dioxide. To find the odds that radiation, as it's coming up from any single location, as that radiation is coming up, what are the odds that the first molecule is going to be carbon dioxide? Well, the odds are, you start with the number of carbon dioxide molecules, 3.54 times 10 to the 21st, and then you would divide it by the total number of air molecules. And you find out that the chances of the first molecule being carbon dioxide, so as that radiation just comes up off the ground, the first molecule being carbon dioxide will be this number divided by that number. And it's a very small chance. The chance is 0.000132. That's a tiny chance that the very first molecule is going to be carbon dioxide. Now we take 1 and subtract this, and that gives us the probability that it's not going to be carbon dioxide. And the probability for 200 parts per million is 0.99987. the probability for today's level of carbon dioxide, 0.99974. And for 800 parts per million, the probability is 0.99947. So what that means is there's a 99.99% chance that the radiation, the first molecule it encounters, is not going to be carbon dioxide. So that's very good chances, 99.99, that it's not going to be carbon dioxide. Well, then how do we figure out if the second molecule is going to be carbon dioxide? Well, we have to take the odds of the first molecule, of one molecule being carbon dioxide, which is 99987, and multiply it by the same thing, 99987. And what you'll find is this is multiplying by a little bit less than 1. So now our odds are not going to be quite as strong that the second molecule is not going to be. And that makes sense. The first molecule is probably not going to be carbon dioxide. The second molecule, there's a slightly more chance that it would be carbon dioxide, but still very, very low. To encounter the third molecule, you'd have to multiply it again, and so on and so on and so on. So how many molecules is it going to take before we can be almost certain that we're going to hit carbon dioxide? So to find the probability that you're not going to hit carbon dioxide, you would take this number and raise it to the power equal to the number of molecules you want to try. So if you want to encounter the first 5 molecules, you'd put this to the 5th power, and that would give you the chances of it not being carbon dioxide. The chances of it being carbon dioxide then are 1 minus this. That'll give you the chances of it being carbon dioxide. Well, it turns out that if you go through 69,970 molecules, you're going to have a 99.99% chance of hitting CO2 within that many molecules. And this is how you'd figure out the probability. You take the chances of not hitting the molecule times the number of molecules that you want to go through, then take 1 and subtract that, and you get a 99.99% chance of hitting carbon dioxide within this many molecules. Now that sounds like a lot of air molecules. If your radiation and you're traveling from the ground up, how far would you have to go to encounter 69,970 molecules to have a 99.99% chance that you're going to hit carbon dioxide? Well, it turns out that if you take the total number of molecules in a cubic meter of air, and you take the cube root of that, you'll find out how many air molecules there are in 1 meter of length. And then you just take this number right here, divide it by that number, and you'll find out how many meters you'd have to go through to reach this many molecules. Well, the answer might surprise you. At 200 parts per million, coming up from the ground, to reach this many molecules, you have to travel 0.2336 millimeters. That's less than 1/4 of a millimeter before you have a 99.99% chance of hitting carbon dioxide. At higher concentrations, at today's concentrations, that distance is even shorter. So what that tells us is that infrared radiation coming up from any location is going to encounter carbon dioxide within the first 1/4 millimeter at any concentration. So it's very likely that carbon dioxide is going to absorb the radiation very close to the ground, within a 1/4 millimeter, at any concentration. In all three concentration levels, 200, 400, or 800, 9.18 times 10 to the 18th CO2 molecules is going to absorb all the available radiation coming up from the ground, all of the radiation that's close to 15 micrometers, within a 1/4 millimeter of the ground. Increasing carbon dioxide does not increase the amount of energy absorbed. All of it is absorbed that comes up off the ground. The amount absorbed today is the same amount that would have been absorbed in pre-industrial times, and it's the same amount that would be absorbed if we double CO2 in the atmosphere. It's all absorbing the same amount of energy coming up off the Earth, because it's all absorbing all the available radiation strongly around the 15 micrometer wavelength, okay? But at all concentrations, it's doing it within the first 1/4 millimeter. Now, when carbon dioxide absorbs radiation, that little molecule's temperature goes up, and it goes up about 1.43 Kelvin. That's how many degrees each little carbon dioxide molecule goes up. So at 200 parts per million, this many molecules, each one of them gets warmed this much. At 400 parts per million, the same number of molecules absorbs the radiation and gets warmed the same amount. At 800 parts per million, the same number of molecules will absorb the same amount of radiation within that first 1/4 millimeter and warm up the same amount. At each CO2 level, the same number of carbon dioxide molecules gets warmed the same amount by the radiation coming off the Earth. So changing the amount of carbon dioxide in the air does not change the amount of radiation ultimately that's absorbed, and there's a 99.99% chance that that radiation is going to be absorbed by carbon dioxide within the first 1/4 millimeter of the air. What about back radiation? Back radiation is also called thermal down surface, downwelling long radiation, infrared radiation in a downward direction, or thermal radiation. It turns out that carbon dioxide absorbs about 8% of the radiation coming off the Earth's surface. Well, once the carbon dioxide molecules absorb that radiation, they heat up and then they give off their own infrared radiation. And so about 4% of that is returned back down to the surface, and it's said that that heats up the Earth's surface. Well, the Earth's average surface temperature is 288 Kelvin. So the Earth is giving off about 391 watts per square meter going up from the Earth. If 8% of that's absorbed and then 4% is sent back down, then you're sending back about 15.64 watts per square meter. Now, does that actually raise the Earth's surface temperature? Well, radiation cannot increase surface temperature unless the incoming radiation is greater than the outgoing radiation. So the radiation that's coming from carbon dioxide back down to the ground is not actually raising the Earth's surface temperature. Now, it is slowing it down from cooling. Instead of cooling at this rate, 391 watts per square meter, you would subtract 391 minus 15.64, and that's how much the Earth would be giving off in total. So in order to raise the Earth's surface temperature, this back radiation can't do it. What happens is the sun comes out every day, and all of a sudden the radiation from the sun means that this radiation coming in is now greater than the radiation going out, and the Earth's temperature rises. And then when the sun sets, the outgoing radiation is greater than the backgoing radiation, and the Earth cools again. So back radiation, unless it's more than the outgoing radiation, cannot actually raise the surface temperature, but it can slow it down from cooling. So if we increase carbon dioxide levels, does that mean we're going to intercept more radiation and send back more radiation and make the ground cool even slower so that it raises the average temperature? Well, we know that it takes a certain number of molecules. We already showed that it takes a certain number of molecules to absorb all the radiation coming from the Earth, which would be the full 8%. And even at 200 parts per million, that happens within the first quarter of a millimeter. At today's level, again, the same number of molecules are going to absorb the same amount of radiation and send back the same amount of radiation. If we double CO2, it's still going to be the same number of molecules absorbing the same amount of radiation and sending back the same amount of radiation. And so at all three concentrations, it doesn't matter what the concentration of carbon dioxide is, the same number of molecules will be absorbing the same amount of radiation and sending the same amount back. So by increasing carbon dioxide, you're not going to increase the amount of radiation that's absorbed, and you're not going to increase the amount of radiation that's sent back. Now that leads us to another common fallacy, and the common fallacy is that greenhouse gases are the only gases that can send radiation out into space. All right, so greenhouse gases include carbon dioxide, methane, water vapor. All right, and so it's believed that by many people that these molecules are the only ones that can send radiation out into space. The truth is, only greenhouse gases will intercept some of the radiation, okay? But every single gas in the atmosphere, including nitrogen and oxygen, give off thermal radiation. Infrared radiation is given off by every molecule that has a temperature higher than absolute zero. And it's given off in what's called a blackbody pattern. Now the blackbody pattern is kind of a curve like this, and it's the peak of the curve depends on the average temperature of the molecule. Molecules, when they absorb thermal energy, either by absorbing radiation, which is what greenhouse gases can do, or by absorbing it through contact with another molecule. Molecules are constantly vibrating, okay, and so when they bump into each other, they transfer thermal energy. Thermal energy is the average kinetic energy of the molecule, the average amount of energy that molecule has, which causes it to shake and move and vibrate and bounce off things. So as the air molecules are all bouncing around, they can absorb energy directly by contacting the ground. They can absorb energy by contacting each other. They can absorb energy by being circulated so that they can contact each other. That's called convection. Touching the ground is called conduction. Touching each other is also conduction. And then greenhouse gases have a third way of doing that, and that's absorbing the radiation that's coming up. Only greenhouse gases can absorb thermal radiation, but all gases can give off thermal radiation. Because all atoms that are warmer than absolute zero give off thermal radiation. And so all these molecules can give off thermal radiation into space. That leads to another fallacy, and that's the idea that greenhouse gases trap heat. Greenhouse gases can't trap heat, and here's why. If a greenhouse gas absorbs radiation and becomes warmer, it then has to share that heat with other molecules that it bumps into. And then all the molecules together will radiate that heat. So the heat is not trapped by the greenhouse gas, it's absorbed by the greenhouse gas, shared with other molecules, and then they all radiate it together. Now the average time it takes for the carbon dioxide molecule to absorb one photon of energy and then turn around and shoot off that photon is about 1 second. But in that second, it's going to be struck by nitrogen 5.92 times 10 to the 28th times. And it's going to have to share that heat. So even before it can give off any heat, it's going to absorb the radiation, heat up a little bit, then be struck this many times just by nitrogen, not counting oxygen or any of the other gases, but it's going to be struck this many times by nitrogen molecules and have to share that energy with them. And then all together, they're going to radiate based on how much energy they have. Now, there's been a worldwide study of back radiation done by H. Douglas Lightfoot and Orville A. Mamer in 2017, and I'm going to share the results of that with you now. Okay, so the study of back radiation that was done showed this. The highest place that was measured had a back radiation of 420 watts per square meter, and that was at a place called, I'm not sure how to pronounce this, but I must go for it, Kwajalein or Kwajalein Atoll in the Pacific, near the equator. At Kwajalein Atoll near the Pacific, this much back radiation was coming back. So we'll call this back radiation, B for back radiation. 420 watts per square meter was coming down from the atmosphere. Now, here's what we know. We know that it isn't just the greenhouse gases that are sending radiation down. Every single molecule in the atmosphere can give off thermal radiation. So if you're measuring back radiation, it's not just coming from greenhouse gases. It's coming from every single molecule in the atmosphere. So every single molecule in the atmosphere was sending radiation back to the Earth at 420 watts per square meter. Now the average, this was the highest amount measured of back radiation. Now the average high temperature at that location, at that atoll in the Pacific, is 304 Kelvin or 88 Fahrenheit. That's the average high temperature. At that temperature, the Earth is giving off 486 watts per square meter. So you can see that the high measured back radiation is actually lower than what the Earth is giving off at that location on its average high. And so 486 minus 420 would give you about 66 watts per square meter leaving the Earth. Okay? And that means that if this radiation is coming from all the air molecules, then the air above this location, the whole column from the ground all the way up, averages the average temperature of every air molecule in that column is about 68 Fahrenheit. This makes sense. If the Earth's high temperature is, if the ground is 88, all the air above the ground is going to be cooler. It's going to be absorbing some of that radiation, or some of that, not just the radiation, but it's going to be absorbing some of the heat by contact. But then it's going to be giving off some of that heat into space. So we expect the air to be cooler than the ground on average. And sure enough, even where the back radiation is highest, the ground radiation coming off is still more than that on average. Now, the only time that this would not be true would be as if you had warm air coming over a cool location. Warm air is going to give off more radiation than the ground is. If the air is at a higher temperature than the ground, then the air is going to heat the ground up. But that doesn't happen on average. Okay, on average, the radiation coming off the ground is going to be more than the radiation coming back, because the Earth is absorbing heat from the sun in terms of visible light. Then it's giving off infrared heat to warm the atmosphere, and then the atmosphere is giving it off into space. So the atmosphere is acting like a blanket between the Earth and space. And so the Earth is going to be warmed by the sun the most. Then the atmosphere is going to be a barrier, which is partly warm from the Earth and then partly giving off heat into space. So it's going to be, on average, a lower temperature than the ground. And then space is going to be the coldest of all. All right, so that's how the heat flows, and this is how this is what they measured when they were measuring back radiation. Well, they took the lowest measuring of back radiation was 96 watts per square meter, and that was at the South Pole. The average low temperature at the South Pole is about minus 76 Fahrenheit, or 213 Kelvin. At 213 Kelvin or minus 76 Fahrenheit, the average low temperature at the South Pole the Earth is still giving off 117 watts per square meter going up into the atmosphere. The atmosphere is giving back 96 of those. This is what was measured, okay, coming back. And so the air temperature above the South Pole would be minus 94. Well, if the ground temperature is minus 76, we would expect the air temperature to be colder than that, minus 94, and then space to be even colder than that. And so that's the back radiation at the South Pole. What about the average? The average radiation I calculated from the U.S. standard atmosphere. I took the U.S. standard atmosphere and took it in 100-meter increments and averaged all the air molecules, their temperature and their pressure to find out what the average temperature would be. So at the Earth's surface, the temperature is 288 Kelvin or 59 degrees Fahrenheit. That means that the Earth is giving off 390 watts per square meter. The average atmospheric temperature, if you average all of the temperatures in the U.S. standard atmosphere from ground up to 100 kilometers, okay, is 250 Kelvin. That's the average air temperature over the Earth, which is minus 9.7 Fahrenheit. So if the ground temperature is averaging this much, the average atmospheric temperature is this much, that means that the atmosphere would be sending back 221.5 watts per square meter on average. In each case, the Earth is giving off more than what is coming back from all the atoms in the atmosphere. Here, this is the highest one that was measured. Okay, the Earth is still giving off more than what's coming back to it. The coldest one, the Earth is still giving off more than what's coming back from the atmosphere. The Earth is still giving off more on average than what's coming back from the atmosphere on average. And that's how back radiation works. Back radiation means that the Earth is going to be, the cooling of the Earth is going to be slowed. All right? And so the atmosphere acts as a blanket so that the Earth is warmed by the sun. Earth is warmed by the sun. And then it's going to give off that radiation. It would cool very quickly, except the atmosphere absorbs some of that radiation and sends it back. And so the Earth cools slowly. Now, increasing the amount of carbon dioxide or greenhouse gases is not going to increase the amount of energy that's absorbed, because all of the energy that can be absorbed is absorbed off the Earth's surface, shared with other molecules, and then given off again, and eventually given off into space. Now, there's a fear out there that if carbon dioxide concentrations increase, then CO2 molecules are going to have to radiate into space at higher altitudes. And here's how that would work. If you have a bunch of CO2 molecules and the radiation comes up from the Earth and gets absorbed by all of them, and as we found out, that's probably going to happen in the first quarter of a millimeter. All right, but then they will share their radiation with all the other molecules, and it reaches a certain altitude. You know, let's say that there's a carbon dioxide molecule here, and it shoots its radiation up, and that radiation, some of that's absorbed by another carbon dioxide molecule. Well, it's going to reach a level eventually when it can just shoot straight up into space and not be absorbed by anything. And the fear is that if we increase the carbon dioxide levels, then that's going to be absorbed at a higher altitude, and the carbon dioxide molecule that's up there is going to have to shoot it off at a higher altitude and a lower temperature. And if the carbon dioxide molecules are radiating at a lower temperature, okay, then the surface temperature, in order to get rid of the energy, the surface temperature is going to have to rise, because the radiation up here is leaving at a colder temperature. And so there would be less energy coming out of the CO2 molecules, and so the Earth's temperature would have to rise to compensate, so that the incoming energy will balance the outgoing energy. That's the fear. Right now, 15 micrometer wavelengths, remember that's the wavelengths that are absorbed by carbon dioxide, are heading into space at an altitude of about 5 to 9 kilometers. Okay? If you double CO2, then the altitude is going to be 11 to 13.9 kilometers, and at that altitude, the temperatures are lower. And so the fear is the Earth's going to have to warm up to compensate for those CO2 molecules that can't get rid of their heat or can't get rid of their radiation until they get to a higher altitude, and then they're going to be getting rid of it at a lower temperature. But what will happen to that radiation? The radiation that would have been given off at the 15 micrometer wavelength is going to come up and be absorbed by a CO2 molecule. That's going to raise that CO2 molecule's temperature slightly. That CO2 molecule is then going to bump into other air molecules, and they will release energy at other wavelengths that will actually compensate for the lack of 15s. So here's what happens with greenhouse gases. The carbon dioxide will absorb it at the 15 micrometer wavelength. It will then share energy with all others, and they will give off energy at other wavelengths. So it's almost like a banker who collects all the $20 bills and gives you $20 in return, but not in $20 bills. What's going to happen? All the $20 bills come out of circulation, but then all the other denominations of bills increase in circulation. And this is exactly what happens with the radiation. Even though radiation is absorbed at the 15 micrometer wavelength, it's given to other molecules, the heat is given to all molecules, and then all the molecules together radiate the heat again. And what this does is it causes a depression in the 15 micrometer wavelength, but a corresponding surplus in other wavelengths. And so the total amount of energy leaving the atmosphere, yeah, the 15 micrometer wavelengths are going to be leaving at a higher altitude, but all the other wavelengths are going to be leaving at a lower altitude and compensate for that. So there's going to be the same amount of energy leaving the atmosphere as was before. It's just going to be in other wavelengths, not in the 15 wavelengths. The concern that 15 micrometer wavelengths are going to be released at a higher altitude and cause surface heating then is based on the idea that only the Earth's surface and only greenhouse gases can send radiation into space. And that's the same fallacy that we've dealt with before. And that is the fallacy behind the fear. The fallacy is that only carbon dioxide and other greenhouse gases can radiate into space. The truth is, not only does the ground radiate into space and the greenhouse gases, but every single gas molecule can radiate thermal radiation, give off thermal radiation. They can't all absorb thermal radiation. They can all absorb thermal energy, thermal heat energy but then they can turn around and they can all give off thermal radiation based on their temperature. And so the radiation going into space doesn't have to be at the 15 micrometer wavelength. It can be at other wavelengths, and we'll see this in a minute, where even where there's a depression in the 15, there's a surplus in all the other wavelengths that compensates for that. And this would be the same thing if we increase carbon dioxide. It's not going to change the total amount of energy that leaves the atmosphere. And it's not going to cause surface heating, because even though there's a depression in the 15s, okay, and so that the 15s are released at a colder altitude, there's going to be a surplus, a corresponding surplus in the other wavelengths that are released at a lower altitude. Now, to illustrate this is a satellite radiation profile over the Pacific, okay? So this was taken up over the Pacific Ocean, and it shows all the wavelengths. This jagged line here shows all the wavelengths of radiation coming up from the Earth's surface and coming out of the atmosphere. And what we see here, this is 15 micrometers, okay? And so we see a huge depression here that is carbon dioxide absorbing the 15 wavelengths, okay? And then we see other wavelengths. We see another depression here, okay? And this is kind of depressed, and the whole thing's curved up like that. Now, typically what you see they'll highlight a line near the top of this graph, okay, and say that, well, this would be the surface temperature, and then you can see all the trapped heat that's trapped by greenhouse gases, and that's typically how they deal with these things. But the reality is, since this is the radiation coming from all of the atmosphere, then the total energy coming out of the atmosphere is going to be the average temperature of the atmosphere that's being measured. So the column of atmosphere that's being measured, all the radiation coming up from the ground up and reaching space is what's measured here. And the total amount of energy here is going to be the average temperature of the air column being measured from the ground up. So we take, so then if you add up all of the energy that's under this curve, okay, you get a different story. When you add up all of the energy that's underneath the curve that's coming up from the ground up, okay, it's the same thing as what would be the area underneath this blackbody curve. And so the sum of the energy coming up off the Earth's surface is equal to this green line. That green line is at a temperature between 270 and 280 Kelvin. Okay, so that means that the temperature of the air column being measured is between 270 and 280 Kelvin. And now what this reveals is, yes, you have a depression caused by carbon dioxide, but you also have surpluses caused by sharing the heat with other molecules, which then give off their heat at all of the wavelengths in a blackbody pattern based on their temperature. So even though there's a depression in the greenhouse wavelengths, there's a corresponding surplus in other wavelengths, okay, that equals the total temperature of the atmosphere. So the net effect of greenhouse gases is to absorb certain wavelengths, share that heat with all the gases around them, and then all the gases and the greenhouse gases together give off radiation in a blackbody pattern based on their temperature, causing a resulting deficit in certain wavelengths that are absorbed, but then a corresponding surplus in other wavelengths that aren't absorbed. So what are the conclusions of this video? Well, first of all, if we increase carbon dioxide concentration, we will not increase the heat in the atmosphere. Because if you remember, it's going to take the same number of carbon dioxide molecules to absorb all of the available radiation coming from the ground, whether that concentration is 200 parts per million, 400 parts per million, or 800 parts per million. It's still going to be the same number of molecules absorbing the same amount of radiation. There's a 99.99% chance that radiation from any location on the Earth is going to strike carbon dioxide within a quarter of a millimeter, whether it's at 200 parts per million, 400 parts per million, or 800 parts per million. Back radiation can't actually raise the ground temperature unless it's more than what the ground temperature is emitting. And we saw that worldwide, from what's been measured on average, the Earth is giving off more heat than the atmosphere is returning to the ground. The one exception is when warm air moves over cold ground. When warm air moves over cold ground, then the air can warm the ground. In all other cases, the air, including all the greenhouse gases and all the other gases, the Earth is warmer than the air on average, and so the Earth is warming the air, and then the air is giving off energy into space. The air does slow down the Earth's cooling, but all the air molecules are doing that. Radiation is coming from every air molecule, not just the greenhouse gases, and that's very important to remember. Only greenhouse gases absorb thermal radiation, but all matter can absorb thermal energy, and all of the air molecules absorb thermal energy by direct contact or convection, and the greenhouse gases absorbed by radiation. All matter then can turn around and give off thermal radiation, and it all does if its temperature is higher than absolute zero. It will give off thermal radiation, and it'll give it off in that smooth curved black body temperature pattern that we saw on the graph. Back radiation then is a combination of the radiation of every air molecule, not just greenhouse gases. Since every molecule is radiating, the charts that we see record the energy coming from every air molecule, not just greenhouse gases. Since that's the case, then on those same charts, the total amount of energy that's recorded is the total amount of energy coming from the atmosphere, which means it also corresponds to the average temperature from the ground up of the air column being measured. And since that's the case, if we then add up all that area, all of that energy, and we make a smooth black body curve that corresponds to the same amount of energy, then what we see is we see a deficit in certain wavelengths and a corresponding surplus in other wavelengths. And that's what greenhouse gases do. That's the end of this video. Thank you for watching. The next video will go over the history of climate change, the geological history of climate change, and then we'll go over what could be done about climate change, and then we'll discuss how to apply some of this knowledge to other planets and would that have atmospheres, and also how to understand the moon's temperature based on the things that we've learned. So thank you for watching. I hope you have a great day.